o'clock. So let's see, let's get started. I posted a new homework assignment. It says due October 22nd because apparently I can't add 16 and 7 correctly. October 22nd is tomorrow. It's not due until Friday. Okay, so it's October 23rd is what it should say. But anyway, that's posted on Blackboard and has been since today. Okay, and the homework this week involves more curve sketching problems and some optimization problems. Okay, which we're talking about optimization now. Any questions before I get started? Okay, I'm going to share my screen and we're going to work some optimization problems. That's my next class. All right, so here's a problem. Yeah, the optimization problems, you have to take each one as it comes. Okay, there's no set way to go about them. You just have to read the problem. I like to draw a picture if possible, and figure out what it gives you, figure out what it wants you to find, and set up your relationships and go from there. So we worked the farmer wanting to have the maximum area field under certain conditions. That was Wednesday. That was a long time ago. But here's another one. A cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay. So, well, okay. A cylindrical can, so it's a cylinder, and that means that, let's see. Let me let somebody in. Okay. Well, what's the volume of a cylinder? And also we need to know the surface area. Okay. The volume of a cylinder, well, you've got your radius and you've got your height. And the volume of a cylinder is the area of the top of the can multiplied by the height. So pi r squared h. Now volume, okay, that's fixed in this problem because we want the volume to be 1 liter. So 1 is pi r squared h. Yeah, we're not finding the volume. The volume's given. But that does give us a relationship between r and h. That says that h is 1 over pi r squared. And I'm going to need to, well, not have 2 variables. So that's going to allow me to write h in terms of r and not have to deal with h. Okay, but what we want to minimize is the cost of the metal to manufacture the can. So that means we want to minimize the surface area of the can in order to do that. Now, okay, in these problems, you don't want to, you want to make the simplest assumptions possible. So, okay, if the metal costs more for the top and the bottom than it did for the sides, then you'd have to take that into account. But we're going to assume they're using one kind of metal for the top and the sides. And that means minimizing the cost of the can is the same as minimize the surface area of the can. So we need to know what the surface area is. I'm going to call it SA. And the surface area is, okay, the area of the side plus 2 times the area of the top. Well, because the top and the bottom will have the same area. Okay. So what's the area of the side? Oops. That is going to be 2 pi r times h. And how do you do that? Okay, so just the side. So that's this stuff right here. Think of this can. Okay, cut along one vertical line there, and spread the can out. And what would you have? You'd have a rectangle. So cut, and that would give you a rectangle. And well, this length, okay, that's the circumference of the circle. So that's 2 pi r, and then it has a fixed height. Okay. So the area of the side is 2 pi RH. The area of the top, oh, I set it up there already. That's the side. The area of the top and the bottom, oops. Well, that's the area of the top circle. Okay, that would be, area of the top is pi r squared, and then you got the bottom too, same area. So that's 2 pi r squared. So the surface area is the sum of those. The surface area is 2 pi RH plus 2 pi r squared. Okay. And this is what we want to minimize. Okay, any questions so far? Okay. Well, we're going to need to use this because let me write it down before I forget it. Yeah, as it is now, this is what we want to minimize, but we got a variable of r and a variable of h. And we don't know how to handle 2 variables. Actually, you'll learn something about that in 3rd semester calculus, but it's a bit much for us. So we have this other relationship. We know that the volume of the can is supposed to be 1 liter. So H has to be 1 over pi r squared. And that's going to allow me to get rid of the H in the equation. Okay, you could just as well eliminate the R and have only H left. Eliminating the h is a little bit easier. Okay, so that gives me surface area is 2 pi r times 1 over pi r squared plus 2 pi r squared. And let's see, I may as well do a little math here, a little simplifying. Pi go out and one of the r's. So 2 over r plus 2 pi r squared is the surface area. Let me know if I make a math error, please. Okay, arithmetic error. I'm good at it, and I like to catch them fast before I get to the end and the problem doesn't make any sense. Okay, so, well, actually, to my way of thinking, the hard part of the problem's now done. Got this basic relationship. All we need to do, well, is figure out what r's makes sense. Certainly, you want r to be greater than 0, okay? But I don't see any other constraints because, yeah, you want this can so it's got the smallest surface area, but you can make it real tall and skinny like that, or you can make it real short and fat like that. And the question is, how should we pick this r so that the surface area is the smallest? Okay. All right, so r has to be greater than 0. But now we can use calculus to find the minimum and find which r will give us the minimum. Okay, so I'm going to take the derivative. Okay, so that 2 over r, I could write as 2r to the minus 1 and not have to use the quotient rule. Okay, so minus 2r to the minus 2 would be the derivative of 2r to the minus 1. And the derivative of 2 pi r squared would be 4 pi r. Okay. So that's equal to minus 2 over r squared plus 4 pi r. And let's see. I want to set that equal to 0. So having it written as a product, or in this case as a fraction, will be easier. I'm going to get a common denominator here, okay? And that would be r squared. So it'd be minus 2 plus 4 pi r times r squared all over r squared. Oh, gotta let somebody in. All right. Okay. And when is that equal to 0? Well, it's not defined when r is 0. Okay. But we're not, r equal to 0 wouldn't make any sense here anyway. That would get, well, it wouldn't make any sense because if r is 0, the volume of the can is 0. And the volume has to be 1 liter. So r cannot be 0. That critical number is left out. R can't be less than 0 either. That wouldn't make any sense. What can be 0 is the numerator. Okay, so this says somebody else entered. Okay. Okay. Okay, so that says that I already let him in. Me talking to my iPad. Okay. That says that minus 2 plus 4 pi r cubed is 0. Let me make sure he's in. Okay. I guess so. Which says that 4 pi r cubed would be equal to 2, which says that r cubed is 2 over 4 pi, which is 1 over 2 pi, and that r would be the cube root of 1 over 2 pi, which is the same thing as 1 over the cube root of 2 pi. Okay, so I got an r here. It's positive, so it's a possibility. I need to make sure that this really does give me a minimum. Okay, so, well, I'm going to check my number line. There's 0, but nothing over here makes sense. In fact, 0 itself doesn't make sense. We have this value of r, 1 over the cube root of 2 pi. And let's check intervals. If this really is a minimum, I should get decreasing on the left and increasing on the right, but let's see. Okay. Well, it all depends on what happens with that numerator, because r squared is always positive. Okay, so if I let, let's see, what's the cube root of 2 pi? Well, 2 pi is over 6. The cube root then is bigger than 1. How about I look at 1 over here? 1 for my number to check. That's, no, 1's not, okay, it's 1 over the cube root. Okay, so that's less than 1. So no, nope, 1 won't do. Let's see. Okay. Oh. Well, what if I just looked at 0? Now that's not included, but as far as the function goes, that's not a problem. It's only because of my constraints here. If I put in 0, I get a -2 here. Okay, so that's negative. And that means the function decreases over there. Then if I put in, oh, okay, it's easy to find a number that's bigger than 1 over the cube root of 2 pi. How about 10? Okay. If I put in 10 for r, that's going to give me a really big number for 4 pi r cubed, and so subtracting 2 makes it positive. Okay, it really is a minimum. So the minimum, we get the minimum surface area when r is equal to 1 over the cube root of 2 pi. And okay, what are your units? I don't know. I guess you could convert them to centimeters or whatever, but that would mean changing liter over to cubic centimeters, and I'm not going to bother. This would be basically 1 over the cube root of a liter. That unit, I'm not going to worry about it. Stop that. Okay, well, that's the problem is for the dimensions that would give the minimum surface area. Yeah, the dimensions. So we found r. Well, then h, okay, h is that. H is 1 over pi r squared. which is 1 over pi times the cube root. Oh, no, wait, let's see. Let me just, okay. I want to square this. Okay, so let me come up here. This is 2 pi to the minus 1/3. So r squared would be 2 pi to the minus 2/3, which is 2 pi to the 2/3 over pi. And that's good enough. I guess I could simplify it some more.
Two thoughts.
Okay, you kind of faded out, Mr. Levy. Say it again.
Wouldn't it be pi over 2 pi to power of 2 over 3? Because the power is with the 2 pi.
Yeah, but okay. Okay, r is 2 pi to the minus 1/3. Do you agree with that?
Yes, ma'am.
Okay, so I want to replace, well, then r here is in the denominator.
Mm-hmm.
Okay, so r squared without it being in the denominator would be 2 pi to the minus 2/3, right?
Mm-hmm.
And then, okay, so, but it's in the denominator, so I put it there. Okay, so do you agree with this?
Yes, ma'am.
Okay. And then I can also write that this way, right?
But wouldn't it be the 2 pi? That should be in the denominator. Because I know that from when we were doing the derivatives and such, if, for example, a x, if one of the variables was set to a negative value, you would move that to the bottom, to the denominator, not to have whatever was connected to it move to below it.
Okay, so, well, okay, I don't see what's wrong, but let me go through it again. Okay, so we got r is, okay, because I do make errors, therefore it pays to question my arithmetic sometimes. Okay, so we came out with r is 1 over the cube of 2 pi. So that is the same thing as 2 pi to the minus 1/3. Okay. And that means that if I square r, well, that's 2 pi to the minus 1/3 squared. So you multiply your exponents. 2 times minus 1/3 is 2 pi to the minus 2/3. But that's just r squared. But then h has that r squared in the denominator. But this is r squared, right? So that goes,
Yes, ma'am.
okay, in the denominator. But then if it, since it's to the minus 2/3, okay, let me put in the next step. Let's see if this helps. This would be 1 over pi times 1 over 2 pi to the 2/3. Do you agree with that?
Yes, ma'am.
Okay.
And
But then
so
I've
wouldn't
got,
that be equivalent to pi over 2 pi to the power of 2 over 3?
I don't think so because, okay, so
Oh,
we got,
I mean, what do you have in the denominator? But wouldn't that pi times that 1 over 2 pi here to the power of 2/3 be equivalent to pi over 2 pi to the
yeah,
power of 2/3?
yes, yes. And so I've got a complex fraction here. So that's going to be 2 pi to the 2/3. Okay, this times this over pi times 1.
Wait,
Okay.
wouldn't that be the value for C?
See?
Yeah, because it's, if you have A over B over C over D, you would multiply the A and the D and then set it over the B and the C.
Right. So,
Mhm.
okay. That big, the one is in the top, and that's really 1 over 1.
Mhm.
And then I've got pi over 2 pi to the 2/3. So 1 is A, B is 1, C is pi, and D is 2 pi to the 2/3.
Okay, thank you.
Okay. Well, thank you for asking. Okay. Let's see. I guess you could simplify a little bit more. In fact, let's see. This is 2 to the 2/3 times pi to the 2/3 over pi. Or maybe it's not worth it. Let's see. This would be the cube root of pi. This pi and that pi. Okay, simplified. Which is, okay, the cube root of 4 over the cube root of pi. And I guess you could keep fooling around with it. But all right. We could just leave it like that too. So you should make RB 1 over the cube root of 2 pi and HB 2 pi to the 2/3 over pi. And what would the volume, well, volume we know, okay, so the surface area, well, it's not really a pretty number. Okay, and the units here, didn't really worry about them, but it would be liters to the 1/3, okay, which is not a standard unit, okay, but whatever. All right, so the surface area, which the problem did not ask you to for, would be 2 over r. Ugh, I don't want to try. It's 2 over r plus 2 pi r. No, 2 pi r. It's this. That was a derivative. 2 pi r h plus 2 pi r squared. do that. I have an eraser available. 2 pi RH plus 2 pi R squared. So that's equal to 2 pi times 2 pi to the minus 1/3 times 2 pi to the plus 2/3 over pi plus 2 pi R squared. So that would be 2 pi times 2 pi to the minus 2/3, and not particularly nice number. 2 pi to the minus 1/3 times 2 pi to the plus 2/3. Well, okay, those would go out. That would be 2 pi to the 1/3. And this is 2 pi to the 1/3. So the minimum surface area would be 2 times 2 pi to the 1/3. Okay. Problem did not ask you for that. It only asks you for R and H. So that's the solution. Okay, any questions? Okay, let me do another one. These problems, okay, the only way you're going to learn how to do them is to get in there and try some yourself. Okay, I gave you 1, 2, 3, 4, 5, 6 for this homework assignment, and these are the 6 fairly simple, I think. I'm going to give you more for next week.
You gave us 7 total.
Okay. 1,
Total,
2,
but
5, 1,
you
2,
gave-
4, 5, 6 total.
No, I got A through G on my paper for 1, and then I got 7 problems on my paper.
Okay, okay, I just printed this off. This is the new homework now.
The new homework?
Yeah, the new homework that I
Yeah,
posted.
October 22nd homework.
Yeah, right. Number 1 is a curve sketching problem. Okay, and that's going to take you some time.
It
1,
says
2,
to sketch the graph of A through G.
right,
And all the stuff to get to be able to do that.
right. That's curve sketching. The last 6 problems are optimization problems. Okay.
Yeah, there are 7 of them. There's 1 through 7, and there are 7 minor problems for 1.
Okay.
You said the last 6.
1, 2, 3, 4, 5, 6. Numbers 2 through 7 are optimization problems.
Okay.
Okay, 1 is a curve sketching problem. It's a number 1 is really going to take you a while. Okay, so get started.
I'm actually almost finished with all but the last 2 of
That's
the curve
good.
ones.
Good. Okay. Okay, so let's do another not curve sketching, another optimization problem. And this
Optimization.
one is to, let's see, let me write it down. The top and bottom margins of a poster are each 6 centimeters, and the side margins are each 4 centimeters. Okay, if the area of printed material on a poster is fixed at 384 square centimeters, find the dimensions of the poster with the smallest area. Whoops. Okay, so here's our problem. We want to minimize the area of the poster. That's what we want to minimize. We're given, okay, several things. The area of the printed material is fixed at, what was it, 384 square centimeters. And we're also given information about the margins. Okay, so I'm going to draw a picture. Here's my poster. And okay, and we want to minimize the area of the poster, but we're given that the printed area, okay, this part, this is where your words appear, that's fixed at 384 centimeters. Okay, and we know, let's see, the margin here, that's 4 and that's 6, right? And that's 6 and that's 4. Okay, so let's see. Well, we have some choices to make. I think I'm going to call this length X. Okay, so this is X for the width of the printed portion, and Y the length of the printed portion. And I know that the area of the printed portion is, okay, X times Y, area of a rectangle, and that's 384. That part is fixed. Okay, and actually that's going to allow me to eliminate either X or Y. I like calling my variable X, so I'm going to eliminate Y. And okay, that's going to be helpful. What's the area of the poster? The entire poster. Well, that's this side length is going to be x plus 8, right? Because you have to take x and then add on the margins. And the length of the entire poster is going to be y plus 12. Again, that's y plus 6 plus 6. So the area of the poster is x plus 8 times y plus 12. That's 1. Okay. And okay, well, now I have an x and I have a y. Be good to get, we need to get rid of one letter without not just throwing away, get rid of it legally. We get that. Now I have area as a function of x. Okay, and I think the hard part is now done. You got this relationship figured out. The rest is just calculus. And also we have to worry about our constraints. Certainly it wouldn't make any sense for x or y to be negative or even 0. Yeah, it can't be 0 because if one is 0, you've got 0 times the number is equal to 384, and that's just not true. So constraints, well, we need x greater than 0 and y greater than 0, but you don't have to worry about y because it's really given in terms of x up there for the problem to make any sense. But let's see. So where does what should we make x be to get that area to be a minimum? Okay, so I'm
sorry to interrupt, but where'd you get the 8 and 12 from? I had to step out to use the bathroom.
Where did I get what?
The x plus 8 and y plus 12 from. I'm sorry. I think I may have spaced out at some point, but I did step out to use the bathroom at some point.
All right. Okay, so x plus 8. Well, x is the length, the width of the printed portion. Y is the length of the printed portion. So that for the entire poster, its width would be x plus 4 plus 4 because the margins are 4.
Oh.
And likewise, the length would be y plus 6 plus 6, so y plus 12.
Oh, now I see. I'm sorry.
That's okay.
I was just making sure I understood.
Okay. So area is, okay, I'm going to multiply it out or expand because, well, you could leave it as it is and use the product rule too. Okay, either one. But x times 384 over x, that would be 384. And then x times 12. And then 8 times 384 over x. Plus 8 times 12. 8 times 12 is 96, I think. Okay. And, well, now it's easy to take the derivative. Let me write that in exponential form so that I don't have to. Okay. and 384. 96 are constants, and therefore their derivative is going to be 0 anyway. Then I've got 8 times 384 times x to the minus 1. Okay. So a prime is 0 plus 12 minus 8 times 384 x to the minus 2. Okay, so let's see. X has to be greater than 0. And I want to get my critical numbers. Okay. Well, 0 is, well, okay, 0 wasn't allowed anyway, so it's not even in the domain. But we do have, okay, 12 minus, really, I can write it in the denominator and then get a common denominator. Which would be that. And now set that equal to 0. And that says, okay, well, the denominator can't be 0. X can't be 0, so x squared is positive for allowed x's. The only way you get a critical number is to set the numerator here equal to 0. And that says that 12x squared, and that says that x squared, I'll do some actual arithmetic here in a minute. Okay. Okay. 3 will go into 12 4 times. And then I can divide 4 into 384. So, okay, 4 goes into 38 9 times. And then, so that's 96, right? X squared is 96. Check my arithmetic. So if that's the case, x should be the square root. Well, normally it'd be plus or minus the square root of 96. But the minus makes no sense here. Not in this problem. So we throw it out. And so x has to be the square root of 96. And let's see. 96 is 8 times 12. Let's see. It's got a 4 in it. I'm thinking, can I reduce it some? You could just leave it as the square root of 96. That gives you 8, gives you 24. Okay. So pulling one square root of 4 is 2. And then it's still got a 4. 4 times 6. So 2 times 2 times the square root of 6. 4 times the square root of 6. All right, so we got a value for x, and it is a possibility. Let's check to make sure it really is a minimum. 0, again, nothing. 0 itself doesn't make any sense, and nothing less than 0 makes any sense here. But we got one critical number, 4 times the square root of 6. And let's see, we can just check the numerator. Well, just check this because the x squared here is always positive. So let's see, if I put in, say, 1, that's definitely less than 4 times the square root of 6. 1 would give me 12 minus a big number, that's negative. So the function's decreasing over there. Put in, okay, 10's over here. I can check that. That would give me 12 times 100 minus, well, make it 100. 12 times 100 squared, that's going to be bigger than that number. That's going to be positive. Yeah, pick a number that's easy to check. So any number will do the entire job. Okay, so this really is going to be a minimum. Okay, you've got a minimum. Minimum at R, not R, X. X equal to 4 times the square root of 6. So the dimensions for the poster. Okay, well, X, remember, was the length, the width of the printed area. X plus 8 is the width of the poster itself. So it's 8 plus 4 times the square root of 6. And Y plus 12, that's the length of the actual poster. Well, let's see, what was Y in terms of X? It was 384 over X, wasn't it? Yes. Y is 384 over X. But we have X. That was 4 times the square root of 6. So it's 384 over 4 times the square root of 6 plus 12. And let's see, I just divided 4 into 3, which I don't really need to reduce it. Yeah, you can leave it like this. It's also 96 over the square root of 6 plus 12. And if having the square root of 6 in the denominator bothers you, it doesn't really bother me. 96 times the square root of 6 over 6 plus 12. And that'll reduce a little bit more. 6 actually goes, it's 16, right? Okay, so you should make for length and width, the length at the Y plus 12, 16 times the square root of 6 plus 12, the width, centimeters, we do have dimensions here. The width is 8 plus 4 times the square root of 6. And that's what the problem asks for. Yeah. What dimensions will give the largest? No. Wrong problem. Okay. What dimensions? Find the dimensions of the poster with the smallest area. And those are the dimensions. Questions? It looks like I am out of time. Okay, so I'm going to spend tomorrow. I'm going to spend tomorrow working some more of these problems. Okay, but you need to go ahead and try them yourself. Yeah.
you happen to know what
That's really the only way you're
day-
going to get a feel for it. Any questions? Okay, class is over. You can leave if you need to. You can hang around for a few minutes and ask questions too. Okay, okay, Mr. Drake.